Swayam Prabha. Digital India. Educated India.
So today we are going to discuss continuous distribution. There are many continuous distributions, but we are going to discuss three of them. One is uniform distribution, exponential distribution, the other one, and the third one is normal distributions. There are many more continuous distributions, but that is beyond the scope of this course. So these three distributions we are going to discuss. First of all, we start with normal distribution. Normal distribution is a very popular distribution and very common. It is also known as Gaussian distribution. This distribution can be defined by two parameters. We have already learned that every distribution can be described or defined by their parameters. Some distribution have two parameters, some distribution have only single parameter also. So normal distribution have two parameters. One is the mean of the distribution and the other parameter is standard deviations, that is sigma of the distribution. Once we know these two values, the distribution will be known to us. The properties of the distribution, this particular distribution, is that the curve is symmetrical. It is bell-shaped and it has infinite range. You can see the curve on the right hand side. So it looks like a bell. Therefore, the name has been given bell-shaped curve. And you can see that it is symmetrical. That is, left hand side from the midpoint, if we see the left hand side and right hand side, both are exactly similar. Therefore, it is perfectly symmetrical. The probability density function is a bit complex and it is stated here. It is fx is 1 upon sigma x root over 2 pi e to the power minus half x minus mu by sigma x whole square. The probability density function is actually describing the equation of the curve. So obviously it is a complex curve and this is the distribution function of the curve. The mean is at the center, it is shown here. Right at the center where the peak appears, that is where the mean will lie. Sigma x in this case is the standard deviations. So we have plotted here a point which is at a distance of sigma x from the mean. So this point is therefore mu plus sigma x. And fx is the probability distribution function. And theoretically, the curve goes to the left hand side towards minus infinity and to the right hand side to plus infinity. So these are the important properties of the curve which you must remember. The area under normal distribution curve basically represents the probabilities of x assuming various values. The notation that is used for normal distribution is n and within bracket we write mu and sigma square. But mu basically means mean and sigma square is the variance. So by writing n within bracket mu and sigma square, that automatically means that this is normal distribution with mean mu and variance sigma square or standard deviation sigma. The total area under the curve is 1. That is total probability. All these frequencies which are here represents the probabilities of a particular value that the variable x takes. So if sum of those probabilities will be always equal to 1. And the probabilities are basically area. And hence the total area is always 1. Now, how do I determine the probabilities? Now, the curve is shown on the right hand side. So, if I want to find out the probability that x takes between the two values of x, x is what? Capital X is representing the variable x. That is, this variable is the normal distribution variable. So x1, x taking values between x1 to x2, what we need to do? We'll take the whatever is the density function of the variable which is fx. Fx dx we have to integrate from x1 to x2. That will give me the probability between x1 to x2. Because we need to find out the area. And now the fx is given here. This is a complicated function. So if I want to know the area between x1 to x2, let us say my x1 is here and x2 is here. And I am interested to know what is the probability that x is going to take between x1 to x2. So that means I need to know what is this area. And therefore I need to integrate this equation from x1 to x2. These are the two limits. Similarly, if I want to know probability that x is going to take values more than x, this x is shown here. So if I want to know what is the probability that the variable x is going to take values more than small x, same function we have to integrate now from x, starting from x to the maximum value that the x can take, that is infinity. Because on the right hand side, this side, it can goes up to infinity. That's why the limit is up to infinity. And if fx is replaced by this actual function tx and then integration if we do, that means basically if I look at the same thing on the normal distribution curve, this basically means I am interested to know this area. This area is P capital X greater than equal to x. This is the area I have to find out then. And to find it out, obviously, then I need to integrate. So you see that this integration is not easy. It is a complex function. And this needs to be carried out numerically. The calculation is very, very tedious. It's not a simple function that I can directly integrate. Or numerical, if we want to do, that also will take a lot of time and lot of labor is required. So it is a very, very tedious process. Now, this difficulty can be overcome by using standard normal distribution. Another term. So normal distribution and standard normal distribution. They are different. You should be gradually familiar with this term, standard normal distributions. So, if I can use this, then all this calculation of area becomes very, very simple. That is what we have to now learn. So, standard normal distribution probability density function of normal distribution, already you know, it is already written in the previous slide also. Now, for standard normal distribution, we have to change the x variable to z variable by the transformation what? Z. This is what we need to do. That is, we have to replace this function x minus mu by sigma by another variable z. If we do so, the curve changes from normal to this is called standard normal distribution. And the equation now looks little simpler. The density function of variable z, which is new variable now, we write it fz. What do we do? This part we replace by z only. It remains 1 upon root over 2 pi minus 1 upon 2 z squared. Z is known as a standard normal variable. That is what the z basically is. So, all standard normal distribution will have a mean 0 and standard deviation 1. So, this is the normal distribution. This one is standard normal. As you change it, the value, so the x variable changes to z variable. The mean, what was mu in the case of normal distribution, whatever is the mu value, that mean in the case of z variable is 0. That means mu z is equal to 0. And the other thing, important thing is that the standard deviation is equal to 1. That is the beauty of this standard normal distribution, that it can be proved also that it has a mean which is 0 and it has a standard deviation which is always 1. And any normal distribution can be transformed into standard normal distribution by simply transforming the x variable by z variable. Now, when it is a standard normal distribution with mean mu equal to 0 and standard deviation sigma is equal to 1, if I want to know, the shape of the distribution does not change. It is still remains symmetrical. The mean becomes 0 and standard deviation becomes 1. So, probability of finding z variable between a and b will be simply exactly same, that you take the density function and integrate from a to b. The constant is 1 upon root over 2 pi. So, that is what we need to do now. This integral cannot be evaluated by ordinary means, since we cannot find a function whose derivative is this. So, still the difficulty is there. Now, what has been done is that numerical integration is used to find out the areas between two limits a and b. So, this has been found out And the Z value has been tabulated by a mathematician called Gauss. So he has done this numerical integration for various values of Z. And then he has given a table to us, and that table is extremely helpful for finding out the probabilities. The term CDF means cumulative distribution function. So one is probability density function, the other one is cumulative distribution function, where phi z would means that the integration limit is, you have to only check, this is minus infinity to z. That means CDF basically means that if I draw the curve here, standard normal distribution curve, then from minus infinity to a particular value of z, this is, let us say, z variable, mu equal to 0 here, and here the sigma is equal to 1. So from this side, this is giving minus infinity to z. I mean, this is the area which has been found out numerically, and these values have been quoted in the form of a table. And that is known as standard normal distribution table. So one such table is shown in this. There are a lot of data. The font size is very small. Now, what is written here is that you can consider it to be Z. In some books, it is written as capital U. In some books, this is capital Z. Z indicating that Z is the standard normal distribution variable. So most of the books writes generally Z. Now in this table, you should first learn what is there in this table and how to read the table, because that is what is required to do the calculations. When you want to know the probability between two limits, or probability greater than a certain particular value or less than a certain value, we have to ultimately find out the probabilities by consulting this Z table. Now in this book, what they have done is that the book has quoted the area beyond Z as shown by alpha. Now we have to remember that this particular graph, which is standard normal distribution graph, this is a symmetrical graph, and therefore from the midpoint, the left hand side is 0.5 and the right hand side is also 0.5. On the midpoint, there are 0.5 on the left hand side and 0.5 on the right hand side. So there is a symmetry. This data has been quoted for Z values starting from, you see here, if you can see, this value is 0. For 0, and the alpha indicates the area beyond that value of Z. So the column here, Z, as you see it here, have different values, and there is a corresponding value of alpha. Alpha indicates the area beyond the value of Z, whatever value has been quoted here. Now if I see the very first value of Z, it is 0.00, and the alpha value has been quoted as 0.5. So why at Z equal to 0 it is 0.5? Now where Z is 0? This is the place where Z is 0. So what does it mean? It basically means that the area of the curve beyond 0 that is on the right hand side of 0, this total area of the cup is going to be half of 1. The total area is 1. So this must be equal to half, and half is equal to 0.5. That's why the data has been quoted here as 0.5. If I take another reading, let us I take a reading this value 0. It is 0.4 here, and the values quoted is 0.3446. I write it again. 0.4 is the value of Z, and the value of alpha is 0.3446. So this is alpha and this is Z. So alpha is the area beyond 0.4. That means Z value 0.4 and beyond, the area of the curve is going to be 0.3446. If I take another value of Z, which is 1.0, then the corresponding value is 0.1587. So there the value is this. That means Z greater than 1, the area is going to be 0.1587. So you will remember that for the standard normal variable, the 0 is here. If we go to the right hand side, the Z value will be only positive. It will be 0.1, 0.2, 0.3, 0.4, 0.5, 1, plus 1, 1.5, like that. Right hand side will be always plus. And if we go to the left hand side, it will be all negative values. It will be -1, -2, -3, like that. It will go on. So once you to do some calculations, it will be clear to you, and you will be able to understand quite fast. This is a table which is reverse, in the sense that here the alpha values are given here, and Z values, corresponding Z values are stated in the second column. So for a given value of alpha, what is the Z? That is given in this table. Previous table is for a given Z, what is the value of alpha? Alpha is the area, and here the area is given. So what is the corresponding Z value? So that way 2 types of tables could be there. You can consult any textbooks and you will find this type of data tabulated there. And also you can find some books, the standard normal distribution tables are quoted from -infinity to a particular value of Z. That also is available in some books. That means in some cases you may find that if this is my standard normal distribution, this basically means that these areas, particular value of Z, this side is -infinity, this side is +infinity, and only -infinity to a given value of Z. Suppose Z is 1 here. So -infinity to Z equal to 1. What is the area? That area has been given. So for different values of Z, Z will be -1 this side. It cannot be, let me rewrite it. Here it may be Z equal to 1. So in some books you may find that they are giving the areas starting from the -infinity to a particular value of Z. So that type of tables also could be there in some books. So, or the other table, as I have already discussed, this kind of table also could be there. So you must be familiar with the type of table which is given and how to use that. The conceptually, if you are correct, then there is no problem in using the type of table, whatever is supplied to you or whatever is available to you. So here, we are trying to show you that how the normal distribution curve to standard normal distribution curve, as we change it, how it looks like. So this is the original curve of normal distribution, the variable x, and when we replace the variable z, which is x minus mu by sigma, we get a curve which is called standard normal distribution curve. So this is the standard normal distribution curve. And this one is normal. This is x scale, this is, remember, z scale. So here we are showing you few lines we have drawn on the x-axis. So for the x variable, the mean is mean here at the center, and then we have drawn some lines here. They are away from the center by 1 sigma. This is by 2 sigma. That's why written 1 mu plus 1 sigma, mu plus 2 sigma, mu plus 3 sigma. This side similarly, this point is mu minus 1 sigma, mu minus 2 sigma, and mu minus 3 sigma. So these are the some points on the x-axis which represent the x variable, and these are the corresponding probabilities which are the height of this curve. Now when you transform it into z variable, you see the mu, the z value becomes now 0 here, because the z variable will have a mean which is 0, and this corresponding, which was mu plus 1 sigma, in terms of z scale, it will have a value z equal to 1. This will be z equal to 2, this will be z equal to 3. This is minus 1, minus 2, minus 3. This will look like this. So when x equal to xi, corresponding zi will be xi minus mu by sigma. So if I write x is mu plus 1 sigma, that is, I take this value, mu plus 1 sigma. And therefore, what will be corresponding z here, which is, let us say, z1. So z1, this particular equation will be used. We replace x by mu plus 1 sigma and then minus mu by sigma. So this is going to be 1. Similarly, for mu plus 2 sigma, that is this particular point, the corresponding z value will be how much? Same thing in this equation, z equal to x minus mu by sigma, we replace x by mu plus 2 sigma minus mu. So mu and mu will cancel, will be left with 2. So I mean this mu plus 2 sigma point here is basically equal to 2 in the z scale. So this is how corresponding the z values can be found out, and the original graph or curve with a certain value of mu and a certain value of sigma can be transformed into a standard normal distribution curve where the variable is z with standard deviation equal to 1 and mean equal to 0. So standard normal distribution curve is a unique curve, whereas normal distribution curve could be plenty depending upon what is the value of mu and what is the value of sigma. There could be infinite number of curves, normal distribution curves. But standard normal distribution curve is only one, and that is unique. Now we'll come to the actual probability calculation. As I said, that it is difficult to do the integration, and therefore to overcome that difficulty, this standard normal distribution curve was basically, that's what the mathematician Gauss wanted to make the calculation easy, and he developed this particular technique. As z equal to x minus mu by sigma, therefore dz equal to going to be dx by sigma, and hence from here you can write dx equal to sigma dz. So if we are interested to know p probability, capital X stands for x variable greater than a value which is small x. This is what we need to actually do. And when we change this part into z, this is what it is going to come. And now we replace this dx by this value. So replace dx by sigma dz. And it goes one step further. This is what we basically get. And this is in terms of now z variable. This particular integration z to infinity 1 upon root over 2 pi to the power minus half z squared dz basically means p value, p which is probability of capital Z greater than a particular value small z. So p capital X greater than small x is equal to p capital Z greater than small z. They are equivalent. That is what is written here. Then they are basically equivalent. Similarly, we can show that p x less than small x is equal to p capital Z less than small z. So that means x greater than x equal to capital Z greater than small z, or x less than x. Exactly same way we can show that this will be equivalent to p of z less than small z. And if I want probability between two values x1 and x2, let us say this value, I want to know the probability. Visually, it means I need to know the area as it's shown by the hatched line. How much is the area between x1 and x2? Probability of x assuming any value between x1 and x2 automatically means equal to z assuming any value between z1 and z2. That means I need to know what is the corresponding value of z1 here and what should be corresponding value of z2 for x2. z1 is x1 minus mu by sigma because z variable is x minus mu by sigma. So z1 is going to be x minus mu by sigma and z2 is going to be x2 minus mu by sigma. Therefore, x1 is mu plus z1 sigma, x2 is mu plus z2 sigma. So p x between x1 and x2, we can write what is x1? x1 is this. So x1 I replace by this value mu plus sigma z1. Exactly bring this thing here and place it. This one similarly, you take it and place it here. Because this side I have x2. If I go to the next step, subtracting mu from both sides. If mu is common, subtract them. So p of sigma z1 less than equal to capital Z, sigma z2. Now dividing both sides by sigma, we are left with what? P of z1, z lying between basically small z1 and z. That means p x lying between, probability of x lying between x1 and x2 is equal to probability of z lying between z1 and z2. They are basically equivalent. This is what you should finally understand, that probability of the variable x lying between any two values x1, x2 is equivalent to probability of the standard normal variable z lying between two values z1 and z2. And how to find out z1, z2? Use these equations to find out what is z1 and what is z2. And after finding out z1, z2, next job will be to consult the standard normal distribution table. Areas under the normal distribution curve. I mean, you may find such kind of plots in many books also, that the same thing we have plotted here. This is normal to standard normal. This is the standard normal. And in the Z scale, the area between minus 3z to plus 3z is 99%, this whole area. Between minus 2z to plus 2z, it is 95%, this area. And between minus 1 to plus 1z, the area is 68%. And z2 automatically means 2 sigma limit. Z3 is equivalent to 3 sigma limit in the for x variable. So this is, you can say, in terms of sigma scale, this is 1 sigma, 2 sigma, 3 sigma. So this point is 1 sigma away from the mean. This point is 2 sigma away from the mean. And this is 3 sigma away from the mean. Because 3 sigma is equivalent to 3 in Z scale, this whole area, that is, this area also is going to be 99% or 95% or 68%, as the case may be. So these areas are also quoted in, you will find in many books that they have given the area, the plus minus 2 sigma, the area is how much? The area is going to be 95% for this curve also. Now we take a practical example which we have taken from a particular book. This book is very useful. The chest circumference of a large sample of men were measured, and the mean and standard deviation of the measurements were found to be 96 centimeter and standard deviation is 8 centimeter. So mean is given and standard deviations are given. Now the questions are coming. Find the proportion of men whose chest is more than 104. Second is less than 100 centimeter. Third is less than 90 centimeter, or between 100 and 110 centimeter. How to find out these probabilities? So what should be the approach? Solution. So x is the variable here. The mu value is 96 and sigma, both are given. I need to know what is px more than 104. So first of all, we'll find out what is the z value corresponding to 104. So z equal to x minus mu by sigma. So x is in this case 104, mu is 96, sigma is 8. So this becomes 1. So z value is 1. Now I need to know what is the probability that x is going to be more than 104. That means it is equivalent to saying probability of z going to be more than 1. They are same. And what we need to do now to find it out, I need to consult the table, standard normal distribution table, where the z values are given For different Z values, the area of the curve is also stated. Area is alpha. So now let us see where is the Z value 1. First try to find out where Z is 1. So I check this column, Z value starting point 0.00 and last value is 0.6. So 1 does not exist in the first column. Go to the second, here you start from 0.6 and as you go down, you come across a value 1 here. Here I get a value 1. So for when the value of Z is 1, the area of the curve beyond 1 is how much? They have given 1587 because this is the area, this is what is stated here. Therefore, after consulting table, Z greater than 1 is going to be 0.1587, which we can see from the table. So we write that around 0.16 or 16% of the people will have chest cut more than 104 centimeter. So there is no need to do any complicated integration. Nothing is required. This table is going to be of great help to us. You only need to know how to consult this table, what is the value of Z, and which area you are supposed to find out. Next problem solution, that P is going to be less than 100. So we again find out what is the Z value when X is 100. It is going to be 0.5. But now point is, you have to be very careful here. Px less than 100. Where is Z? 100 value is where? Here. Mean is here. So the 100 is more than mean. I need to know how many values are there which is less than 100. That means I need to know the area which is less than 100. So the area is shown in this curve by this known hatch line. And corresponding to 100, the Z scale value is 0.5. So Px less than 100 basically means Pz less than 0.5. So we consult the table. Then if where is the value of 0.5 Z? And if I go to that value 0.5, we come over here. Where is 0.5? Here it is 0.5. 0.5 for Z 0.5 the corresponding area is 0.3085. Now remember, the way this table has been designed or the area has been plotted, it is the values of the areas are more than whatever Z values are given here. That means this 0.3085 is the area of this part of the curve greater than 0.5. These areas have been tabulated here. So this area, that is, I can write, if I draw some line like this, this area is 0.3085 as per this particular table, because that's how this table has been made. Area more than certain value of Z. So if I want to know the other side of the area, so what I will do? Because I have to find out values which is less than 100 or less than 0.5. So greater than 0.5 is this much. So less than 0.5 will be 1 minus P greater than Z greater than 0.5. And therefore it will be 1 minus this. And hence the result is 0.69. So 0.69 or 69% people will have chest cut less than 100 centimeter. So it's a common mistake depending upon which table a person is using, that if someone is using this kind of table as shown here, that he quotes the value 0.3085, and the answer becomes wrong, because you have to be very careful that this particular table gives values of the area which is greater than whatever value of Z you get. So if the question, what question has been asked, that also you have to be very careful. If I just change this statement, that find out x greater than 100, then 0.3085 would have been the correct answer. But the question is Px less than 100. So it will be therefore 1 minus 0.3085, that is 0.6915. This is one problem. Another problem we have solved. The other one is now we're coming. The fourth one. The third one I have not solved. The fourth one is that we need to find out values between 100 and 110. How many people's chest guards are lying between 100 and 110 centimeters? So I have given x1 and x2. Okay. Therefore, first we find out what is z1 and what is z2. So z1 is 0.5 and z2 is 1.75. So best thing will be always now for such kind of problems, first draw the curve. Write down where the mean, x scale where the mean is there. And then also write down what are the two values in this case and quoted. So write C where 100 will come and why 110 is going to come. Both are coming on the right hand side of the mean. So once you draw this, possibility of making mistakes will be less. Then just below this, you find out the values of Z and write the values of Z, 0.5 and 1.75 as it is written here. So Px lying between x1 and x2 is equal to Pz lying between z1 and z2. Now we have to find out. Now I am interested in the area as shown in the diagram. No, this is the area I am interested. Table gives me the area which is more than whatever Z value we get it here. So probability of Z lying between this and these two limits, we have to find out. So one is Z greater than 0.5. The other side is Z greater than less than 1.75. So Z greater than 0.5, we go here in this table again. And we find out from 0.5, this is the value. We have seen it earlier also. Corresponding to 0.5, the alpha value or area is 0.3085. That means Z more than 0.5. I mean, this side of the area, from here on the right hand side, entire area is 0.3085. Now, I need to know for 1.75 and 0.5. So, what is the, in the Z scale, 1.75, what is the value of alpha when Z is 1.75? So, we consult this and try to locate where is 1.75. But we don't find 1.75 anywhere. It's not there in the table. So what to do? We have to see the nearest value which is there is 1.74 and 1.76. 1.75 lies in between these two. So we have to go for an interpolation. Now Z 1.74 is, the value quoted is 0.0409 and 1.76, the value quoted is 0.0392. So what we'll do, for 1.75, we'll take the average of these two. And we take the average, the value becomes 0.0400. So for this value, 1.75, the value of alpha, these are the values of alpha. Values of alpha becomes 0.04. For Z 1.74, this is the area. 1.76, this is the area. For 1.75, we simply take the average. That is 0.04. So, to find out Z lying between these two limits is equivalent to what? The difference between these two. Why? Because Z 0.5, the corresponding value, this is beyond 0.5 and this is beyond 1.75. That means area from here and more, area from here and more. These two areas I am getting. I need to know the area between these two lines. So what we do? We simply subtract. So we subtract these two, get a figure 0.2685, and that becomes the proportion of values lying between 100 and 110 centimeter. Percentage wise, it will be 26.8%. So that is how we have to do the calculations. One more example. The breaking strength of a cotton fabric is normally distributed with mean 165 kg force and variance 9 kg force square. The fabric is considered to be defective if X is less than 162 kg force. What is the probability that the fabric chosen at random from a lot will be defective? So I draw the normal distribution diagram and the pick, draw another line, and here I write the mean value, which is 165. And then the variance is given 9, and I take the other value X 162. So 162 will be on the left hand side, so this is 162. Immediately which comes to the mind that we need to know how many readings or how many values may come which is on the left hand side of 162. What is this area? That is what we will be interested. So mu and sigma square given, Z value corresponding to the strength 162 I need to know. So Z is coming -1, so we write it -1. Px less than 162 automatically means Pz less than -1, and we need to find out from the scale what is the value of Pz less than -1 is also equal to Pz greater than +1, because the standard normal distribution curve is symmetric. So the area on this side less than this, that is what we need to know, is equivalent to the area which is more than +1. This area what is will be available in the table. But because it is symmetric, this area will be equal to exactly same to this area. Hence we write it here that Pz less than -1 is equal to Pz greater than 1, being symmetrical, the curve being symmetrical. And this value greater than 1, if we consult the table, we have already done it earlier, this value comes 0.1587. This is table, it is given 0.1587. So same value will be here. So we take this value also as 0.1587. And therefore, we can say almost 15.8% of the fabric will be defective.